All right. Well, it's always great fun for me to be back at TASI. 20 years ago, the World Cup was going on, and Germany was in the ascendance. Those guys who were playing then are now, serving as commentators to this year's World Cup. And I was sitting where you're sitting. So obviously, for lots of reasons, it's fun to be here. Now, I'm supposed to give I've chosen to give what I've termed a theoretical introduction to LHC physics, but that's 5 lectures. And you can't give a theoretical introduction to the LHC in 5 lectures. I mean, to really do it, you would need 3 sets of lectures on different subjects. So I'm not going to pretend to do more than I can do. There are a couple of different types of lectures that one could give, given the requirement of choosing a particular approach. And one approach which I could have chosen is to tell you, and since many of you are interested in these subjects and they're connected perhaps with the more formal topics that you've been learning about, I could have chosen to tell you about all the different types of models beyond the standard model that theorists are thinking about, how those models work, what are the basic equations, what are the basic techniques for calculating in them, and what the predictions of those models are in a sort of general sense. Oh, it predicts this type of particle, or it predicts that type of phenomenon. Now, I think that if you look in the literature, you will more easily find lectures on precisely those subjects, review articles, and so forth. And I think it's also easier, given your backgrounds in general, for you to learn those things on your own or from other people. So there are 2 reasons I chose a very different approach, which is to focus on those things which I think are very rarely summarized in any lectures, and which are precisely the things that you're not likely to come across unless someone sits you down in a situation like this and says, look, these are the things you really don't know that you have to know, but you do. And so that's my goal here. There's another reason why I chose this approach, which is that you're going to have this week 5 lectures from an experimentalist. And there's a big culture and language gap to cross. And part of my goal is to serve as the bridge between the types of things that many of you know and the types of things that you're going to be hearing from Jason starting this afternoon. This is also part of why we reordered the lectures, so I would go first, at least for the first lectures this week, and probably for the last one. So let me just tell you very quickly what I'm probably going to do, although things could shift a little bit. Today I'm going to talk about, remind you, the properties of the standard model and why they lead us to want to build a machine like the LHC. Why is the LHC the machine to build as opposed to some other one? And Jason will flesh that out later. It's important to spend a day on basics. Many of these basic kinematic definitions, the structure of the proton, the different types of hadrons, these are necessary because they play a role in many different senses in what comes to follow. Lecture 3 is sort of a catch-all. There'll be various things in there. It'll depend a little bit on how far I can go, but we need to talk about jets to some degree. We need to talk about how predictions are actually made at the LHC, which is not a trivial matter. And we also need to talk about standard model flavor physics a little bit. Lectures 4 and 5 will be devoted to the question of what the LHC is actually going to do. How do you look for the Higgs boson? And what are the general techniques for searches that those will illuminate? And finally, in the last lecture, I'll talk about beyond the standard model models of various types. You'll be hearing about supersymmetry, and you've already heard about ADS-CFT treatments of QCD to some degree. So you'll be primed for some of these models. I won't have to start from the beginning. You already know a lot of the things that you will already know a lot of the things that you'll need. But my goal here, again, will be to sort of sketch out the rationale behind those models and their basic predictions. I certainly can't go through them in complete detail. That would really be another set of lectures all its own. OK, so one of my first goals is to figure out how much you know in this first lecture so that I aim the rest of the lectures at the right level. So I'm going to start with a set of true-false questions. All right, so I just want to know from each of you whether you think something's true or false. And I'll talk about each of these 4 things later in the lecture and throughout the course. So the first I want to make a statement. The first statement is that a proton is made of 3 quarks, 2 up quarks and a down quark. How many people vote true? How many people vote false? If nobody votes, that's no good. Let me try again. And the lecturers don't vote. How many people vote true? How many people vote false? How many people aren't sure? Okay, nobody wants to admit they're not sure. All right, fine, that's fine. It's clear you're not sure because you didn't raise your hand, so I know already. On average, the quarks inside the proton carry about 1/3 of the momentum of each of these 3 quarks carries about 1/3 of the momentum of the proton. How many people think false? And how many people think true? You're talking about a proton that's flying along very fast. Yeah, but it doesn't matter much. Okay. The only types of quarks you'll find in protons are ups and down quarks. You're not going to find strange quarks or charm quarks or top quarks or bottom quarks. True? False? Interesting. Okay. And quarks are confined and therefore never will escape the proton. True? False. 0. 0 temperature. True? False. Okay. They're all false. So we'll talk about that. Okay. Now, they're all false in the proper sense. Tom doesn't agree, but he doesn't understand the sense in which I mean it. Okay.
Now I do.
Okay. All right, so the first thing we have to do is just review the standard model. How many people feel that, okay, so this is again one of those questions. I just want to get a feel for things. How many people feel that they could, without looking at a book, just right now on a piece of paper, write down all the particles that are in the standard model and their charges under SU3 cross SU2 cross U1? How many feel you could just do that right now? Yes. Okay, so the answer, I can do it. Nadi can do it, I think. All right. So next question is, how many of you feel that you could write down all the terms in the Lagrangian? I don't mean getting all the coefficients right or all the numbers right, but you should know every term that goes in there. Okay. So a review is necessary, clearly, okay? Which is fine. That's what I anticipated. I mean, you guys have a lot of different backgrounds, you're different ages, and better that we all be on the same page than that I rush ahead. Now, that being said, those of you who really have never seen this before, I'm not going to cover the standard model start to finish, so you're going to learn a little bit about what you need to know here, and mostly what we need for this lecture, this set of lectures. Okay, so one thing you all know is that we live in a world which is well described using 3 gauge groups, color, weak, and hypercharge, and each with its own coupling constant G1, G2, G3, or if you prefer alpha 1, alpha 2, and alpha 3. Which is g squared over 4 pi in each case. And those are running couplings. So we don't assign them numbers except at a particular scale. The really important scales in the standard model are, first of all, the QCD confinement scale, which I'll just call lambda or lambda QCD, and that's around 300 MeV, depending on exactly how you define it. And the other really important scale is the scale of electroweak symmetry breaking, EWSB, electroweak symmetry breaking. And that is denoted V. And that's 246 GeV, about 1,000 times larger. Okay, now what is actually in the standard model? There are 3 generations of matter. Of course, there are gauge bosons for each of these. There are 8 gluons, 3 W bosons, and 1 hypercharge boson. Those, one of the W's and one of the hypercharge bosons combine to give us the photon and the Z, as we'll discuss in a minute. And then there are 3 generations, and in each generation, there's a lepton doublet, Li, which consists of a type of neutrino and a type of lepton. Now, let me be very clear, again, for those of you who've not seen this before. All the fermions that I'm writing here are 2-component, left-handed Weyl fermions. I'm not using Dirac notation because in the standard model, Dirac notation is awful. How many people have seen 2-component fermions used for the standard model? Good. All right, so I'll go through this quickly. Notice there's a typo because this should be +1. I'm not going to write all the numbers down because you have them in front of you. All right, so we've got I assume everyone actually has the notes in front of them? Okay. So let me not waste time writing all those numbers down. And finally, of course, there's a Higgs. Well, more precisely, there's a Higgs sector. We don't actually know what's in that sector. But in the minimal standard model, we have a Higgs doublet. It's a singlet under color. It's a doublet under SU2 weak, and its hypercharge is a half, which in fact is the same quantum numbers as a lepton doublet, if you want to just keep that in mind. Do I have a mistake here? No, this is right. It's not quite the same quantum numbers in this definition. So it's H plus and H0. Okay. H star has the same quantum numbers as L with this definition. Okay, and then from this model with 3 gauge groups, we come down to the world we live in, which has the gauge bosons associated with 2 because of electroweak symmetry breaking. And in electroweak symmetry breaking, what happens? Well, the third component of the W's and the hypercharged boson X combine together to give us the massless photon and the Z. And the W bosons get mass as well. Now, how does that happen? Well, sorry, before I say how that happens, let me remind you that what then happens is that, in fact, electromagnetism is created from a linear combination of the third component of SU2 weak, T3, and hypercharge. So if you take the T3 and hypercharge quantum numbers of each of these particles and you add them together, you'll get electromagnetic charge. Okay? So that's how you remember the hypercharge. You just remember that. Because, for example, for the left-handed antilepton, that's in other words a positron, it has charge 1, so its hypercharge is already fixed for you. And then for something like the lepton doublet, well, T3 is plus a half for the neutrino and minus a half for the lepton. So the average T3 is 0. So take the average charge of these two. That's the hypercharge. Okay. So it's actually pretty easy to remember the hypercharges once you know the trick. Okay. This is the important equation. Okay. All right. Now, of course, this happens through the Higgs mechanism. And what's involved in that? Well, the standard model has lots of terms, but the only ones we need for this discussion are which ones? Do we need the fermions? No, of course. Do we need the kinetic terms for the gauge bosons? No. Not really. I mean, they are there. What we really need is just the kinetic term for the Higgs itself. And the structure of d mu, which is really the important thing. And, well, let's see. Let's be a little careful. H is a 2-component vector, so d mu is really a 2-by-2 matrix acting on this 2-component vector. 2 components being H plus and H0. So we should really multiply d by the unit matrix, 2-by-2. And then we have, it's convenient to pull out a factor of 2, a coupling of the hypercharged boson with its coupling constant G1 times the unit matrix. Now, how does that work? That's because the Higgs has hypercharge a half. So we put a 1 here because it doesn't have any matrix structure. It's the same for H plus and H0. And the 1/2 here soaks up that 1/2. And finally, there's a coupling of the 3W bosons with a matrix which is a Pauli matrix, again with a factor of a half, and that's d mu. Now, from this structure, we can derive all the things about electroweak symmetry breaking that we need. Well, there's one other term we need, although we don't need much about it. There's a potential for the Higgs boson with the standard structure. It has some sort of quartic term which makes it turn up, and it has a quadratic term which makes it turn down near 0, so that the minimum is at some non-zero value. In fact, we don't really care that it's quartic. It could be some god-awful thing. As long as it has a non-zero minimum, that's all we need. And that minimum, of course, is what we call V. Now, I've drawn this with a one-dimensional, as a one-dimensional thing, as though the Higgs were a real scalar. Of course, it's a 4 real component, 2 complex component thing. So this is really a structure which there's actually, well, I could draw it sort of as a so-called Mexican hat, right? Sombrero. We've got a minimum which has a ring, although that ring is actually a sphere in some abstract space. So the minimum for H in this potential is not determined. I can move it by gauge transformations. I can point in any old direction. But I can choose it without loss of generality to point in this direction. And that factor of root 2 is because it's a real component of the Higgs that gets an expectation value, whereas the Higgs, as I've drawn it here, is written in terms of complex H plus and complex H0. And that is the expectation value for the Higgs. Now, what we're really going to do is we're going to define that the Higgs is its expectation value plus fluctuations. And those fluctuations are, of course, very interesting for us. What do they look like? Well, I'll define them this way. A funny-looking G, which is the reason for G will be clear in a moment if you're not already aware of it. And then it's convenient to take the complex component of delta H and write it in terms of its real and real and imaginary parts. Okay. All right, now all we have to do is take this redefinition of the Higgs, plug it into d mu H and then square the thing to see how electroweak symmetry breaking works. So very quickly, let's just write down the key formula, which is that d mu H, well, actually, d mu H has a lot of terms. It's a good exercise to sit down and just write them all out once so you can remind yourself. What I'm going to do in this lecture is I'm going to pull little pieces out of them here and there. But if you want to derive electroweak symmetry breaking and all of its consequences, all you have to know is that with this shift. Excellent exercise for the students. I recommend you try that tonight. So one term which appears there is a term which is just proportional to V. Right? If I just substitute the expectation value of H and don't include this shift delta H, what do I get? Well, there are various terms that don't involve the Higgs boson at all, or any scalar. They just involve the gauge bosons. So there are terms like this. There's a sign mistake here. It should be minus G2 W3 times the column vector 0, 1. And then there's another term which involves G2 W1 plus I W2 times the column vector 1, 0. Now, does everyone see where those two terms come from? Take a moment, take a look. Are there any questions? No questions? You see it all? Everyone's happy? Okay. Good. So now all we have to do is square this thing. And what do we get? We get the square of that term, and we get the square of this term. Well, the square of this term gives us factors like GV over 2 squared times W plus W minus, where I've taken the square root of 2, stuck it under here, and defined W plus and W minus to be this quantity over square root of 2 with a plus or minus sign. And this quantity is proportional to the Z boson, although I need to normalize it properly. Right? Because this is a linear combination which is not as simple as this one. Here I had a square root of 2 because I have two coefficients which are equal to 1. Here I have coefficients G1 and G2, so I need to normalize the field by the square root of G1 squared plus G2 squared. So for convenience, anytime you see this symbol, that just means square root of G1 squared plus G2 squared, just to save me having to write it again every time and time again. Sorry, this is a G2. And so when the dust settles, we have and the Z is a real field. The W is a complex field, so there's an extra 1/2 for a mass term. But otherwise, you see the mass for a W and the mass for the Z are different only by the fact that here I have G2, and here I have the square root of G1 squared plus G2 squared. So that's how you get the W and Z masses without sweating. Well, I'm sweating, but that's because it's hot up here. OK. And not surprisingly, all right, so that's W squared, that's mz squared. And of course, the other linear combination, a mu, which is 1 over square root G2x plus G1 W3, which you can just see by staring at this, right? This should be the orthogonal combination, properly normalized. This doesn't get a mass term, so we have our massless photon. Okay. Now you should check all these formulas. You should try re-expressing them in terms of sine theta, W. Let's see here. Sine theta W is defined to be G1 over this square root. Cosine theta W is G2 over the square root. Tan theta W is G1 over is G2 over G1. No, G1 over G2. Okay. Work that all out at home. It really can be done on one sheet of paper without looking at a book. Okay, now this is all good, all nice equations and everything, but of course there's a loose end. These W bosons and Z boson have acquired a mass, but massive spin 1 particles have 3 degrees of freedom, not 2, the way massless ones do. Where did that third degree of freedom come from? Right? There are these objects. Now, one has to be a little careful with what one says here. We often say these are Goldstone bosons or something like that. These are would-be. Of course, one should be careful also saying Nambu-Goldstone bosons, which I'll try to do thoroughly throughout the course. But writing curly NG all the time is ugly. So these are would-be. And why are they would-be? Nambu-Goldstone bosons. Yeah, it's because of the gauge symmetry. It's the wrong. So one statement you might make is that, well, there's a term in d mu h squared which mixes these things together. So let me say that first. In d mu h dagger, where I put in the vev, times d mu of delta h, there are terms in which a derivative of a would-be Goldstone boson, for example, G minus, combines with, let's say, a W plus and the vev. So this is a quadratic term which says that a W boson, as it's propagating, can mix with one of these G's. And that term can be removed in unitary gauge, or it can be just left present. But it's telling you that really these aren't separate particles anymore. and that these particles have become the longitudinal polarizations of the W boson. Those longitudinal polarizations are going to come back again and again and again. So let me remind you, let me emphasize again, you all know this, but let me say it very loudly. These particles are as much Higgs as they are W. And that's going to be important. The longitudinal modes of the W's and Z are really appearing out of this delta H. And if I took the limit that G2 and G1 went to 0, if I turned off the gauge interactions, these would become physically identifiable particles. In that limit, the W's and Z's would become massless, so they would have 2 degrees of freedom. And the G plus, G minus, and the G0 would become 3 real massless scalars. So we're going to keep track of them, because sometimes the fact that G1 and G2 are non-zero is really not very important. What is important is that these particles are as much Higgs as W. Okay. So that takes care of the G pluses and the G0. Of course, there's also H0. H0 is very important. That is the physical Higgs. It is the fluctuations of V itself. The fluctuations in this potential back and forth are a massive Higgs boson. You can see it's massive. And the mass is determined by the shape of the potential and is not directly determined by V, which is just the position of the VEV. So there's really 2 independent important questions here. What is V? That we know experimentally. And what is the curvature of the potential around V? And that we do not know experimentally or theoretically. And so we don't know what the Higgs mass is, even in the simplest model, and that's why we're looking for it. Now, there are some very interesting things about the Higgs boson which are not always widely appreciated. The Higgs boson has interactions with gauge bosons, like the W's and the Z. But the interactions, at first glance, well, it looks like it's sort of similar to what you would have if you have a charged scalar that couples to a photon. So what are the couplings of a charged scalar to a photon? So for example, if I have a photon and I have a charged scalar phi plus, what are its Feynman diagram? What are its Feynman vertices? Well, there are vertices like this one, where a photon comes in and 2 scalars attach. And of course, there's also a Siegel graph. Sorry, I'm going to try to use dotted lines for scalars. There's also a 4-point vertex, where 2 photons interact with 2 scalars. Now, for the Higgs, there is, again, a Siegel vertex. And you can see that. You just take the d mu h dagger d mu h, substitute in the dh is h0, turn everything off, set everything else to 0. And you'll see there are terms like w plus w minus h0 h0, or zz h0 h0. Those have, nothing funny has happened with those. But there is no interaction of this type. Think about why. What there is, and this is very interesting, is an interaction of this type. And the same for the Z. That's only there because of electroweak symmetry breaking. That's only there because the VEV is non-zero. So this is a very important interaction. It tests whether electroweak symmetry breaking really is there for this scalar that you may have discovered in your experiment. This is a very important interaction. It's proportional to V. In fact, it's proportional to MW times G2. This is easy to see because this sort of interaction, this WW Higgs-Higgs interaction, is present before you do the shift. Before I write that the Higgs is V plus H. So if there's a little h squared term, there's also a VH cross term. And that VH cross term is this one. The V sits in the coupling, which is proportional to MW, and here's the H. So if V is 0, there's no such term. Okay. Now, 2 other interactions that are worth keeping in mind. Not surprisingly, since there's an interaction of this type, there's also an interaction of this type. And that sort of interaction actually is kind of similar to this one, if you think about it.
What gauge are you in?
Right now, I'm just in a gauge where the G's are not zero. Any other gauge is fine for now. It won't affect these vertices at this. I mean, if I start to go into detail of what their structure is, it will matter. But I'm not giving you the coefficient. If I went to unitary gauge, it would matter. But unitary gauge, although it's very, very good for seeing that the theory is unitary, is confusing for other purposes, which is why I'm not using it here. Use unitary gauge when it's good for you, and don't use it when it's not. That's true with all gauges. Unitary gauge is nice because it makes you see that really you could get rid of the Goldstone modes and just not talk about them. But if you try to do calculations in that gauge or try to understand the behavior of some of the physical phenomena in that gauge, you'll have trouble. And that's because in the limit G2 goes to 0, you know those Goldstone modes have to come back. So unitary gauge is singular in the limit that the weak interactions are really weak. And that's a problem for some purposes. Any other questions? OK, so we have this interaction. Now, the Higgs boson does not have interactions of the form like the one I drew here. There's no direct coupling to the photons at tree level. But there is a loop level calculation that you can do, which allows for Higgs. Let me try again. Allows for a dotted line to turn into two wiggly lines. Okay, now the important point here is that this interaction is a renormalizable interaction involving H, W, and W. There is no HAA interaction. This is an H F mu nu interaction. It's dimension 5, not dimension 3 like this one. So first of all, it's loop suppressed. It tends to be small. And second of all, there's some scale which goes out front, which in the standard model you can calculate. Of course, in some new physics model, some new particles might show up in this loop. Maybe there are new particles that couple both the Higgs and also are electrically charged. They'll change this interaction. This interaction is extremely stable. This one, all sorts of things could happen to it. But it's a very interesting one because experimentally, looking for Higgs goes to photon-photon is one of the ways to find the Higgs, so it's important. Even more important, perhaps, is the fact that there's a similar coupling with two gluons. That's not a good way to find the Higgs, but it sure is a good way to make it because we're starting off with a proton collider and we got a lot of gluons. So again, this is a dimension 5 loop-induced interaction. There's no direct term in the Lagrangian, but it's induced by, for example, a top quark, which has both color and couples to the Higgs. OK, that is the gauge sector. Any questions about the gauge and Higgs sector? I'll say a few words about fermions in a moment. Yeah, it's fine. You can find it calculated in the Higgs Hunter's Guide, or at least maybe they don't calculate. They at least talk about the calculation, show the full formula, and it's not a difficult calculation as these things go. OK, now, one of the important things about, well, I didn't finish writing out the table, but you have it in your notes. One of the important things about that table is if you look at it, you realize that there are no fermion bilinears in the standard model that are gauge invariant. There are no two fermions that you can combine to make a mass term. If you like, it's an explanation for why these are the fermions we have. Maybe there are other fermions out there for which you can write mass terms. The masses are way off somewhere. We can't see them. They're way too heavy. But all the particles in the standard model, which are the light ones, of course, those are the ones we've discovered, there's a reason they might be light. You can't write mass terms for them until you have V. Standard model, fermion bilinears are not allowed. by gauge invariance. But for all of the standard model fermions, couplings to the Higgs are allowed. Now, for everything except the neutrinos, renormalizable so-called Yukawa couplings are allowed. And crudely speaking, they take the form L, H, L bar, or Q, H, U bar, or Q, H, D bar with lots of indices. Now, let's be careful. In some cases, it's H that appears here. In some cases, it's H star. And okay, I've been a little bit careless in the notes. I see the way I did this. So I apologize for that. When I've written things in terms of the actual capital H, I haven't been that careful. But when I've written it out in terms of the components, I think I did it right. Okay, so for example, this term here has a term that would couple H minus to L bar, and there are indices here. The neutrino can come from any of the three generations. The lepton can come from any of the three generations. So there's two independent indices here because they're labeling different fields. They're not related indices at all. And then there's some coupling constant, which has indices y, I, k, and perhaps a superscript e or L to remind us that this is the lepton Yukawa couplings. We're going to have the same thing for the down type and up type quarks. And again, just to be explicit, there are terms which involve, sorry, yeah, that's right. And then there's another term. Let me write this again because I didn't write it very well. Let me move the neutrino over. So then I have, sorry, I didn't write the first time. I'm just getting a little lost here. Let's try it again. So what I want to do is move the lepton over. So I have this. I think with a minus sign, although it doesn't matter too much because it's just a phase. And then we have the lepton, H0 star, and finally the lepton bar with a K. Okay. So what does this term do? Not much, because after electroweak symmetry breaking, this turns into a G+. And the G+ is secretly part of the W+. We already know that W's have some interactions with, well, secretly a little bit of the right-handed lepton, left-handed anti-leptons through some very small coupling. The really important thing is this part, because when I substitute in the Higgs expectation value, this turns into a mass term, coupling any of the three leptons to any of the three anti-leptons through a matrix MIK, which is 1 over square root of 2 YIK. Right, so same thing is true for the up and down quarks. I won't bother to write it out. What's important to note here? Well, first of all, this is an arbitrary matrix. But we have two different sets of fields here, the L's and the L bars, the capital L's and the L bars. So I can do rotations on them. I can sort of essentially choose a basis, because I haven't chosen a basis yet. I can choose a basis for the capital L's and a basis for the little L bars so that this matrix is diagonal. And that's obviously a convenient basis for most purposes. And in that basis, the matrix is just M electron, M muon, and M tau on the diagonals. And I can do the same thing for the up-type quarks, and I can do the same thing for the down-type quarks almost. What's the obstruction? So what's the right way to say it? I just told you how I do it. I choose a basis for the L's and a basis for the L bars so that this matrix is diagonal. Here I've got a problem. I only have one Q. That's the point. So I can choose a basis for Q's and for U bars so that that matrix will be diagonal. Or I can choose a basis for the Q's and for the D bars so that that matrix is diagonal, but not both at the same time. Doesn't change the fact that there are eigenvalues of the mass matrices. There are up quarks and charm quarks and top quarks with definite masses. There are down quarks, there are strange quarks, and there are bottom quarks with definite masses, but they're not simultaneously diagonalizable. That's very important for the physics of flavor, which I'll come back to in the third lecture, but I'm certainly not going to do this in detail. If you haven't thought about this before, this is where the so-called Kabibo-Kobayashi-Moskawa matrix comes from. You should learn this now, soon, tonight. Okay, now I've given you, I won't bother to write it out, reminded you what the masses of the quarks and leptons are in a little table at the bottom of page 4. There's a mistake. The strange quark mass should be 0.1, not 0.01. A couple of things to notice is that, you all see the pattern? No, I don't either. Okay. We don't understand these masses. It comes from some pattern of the Yukawa couplings. The Yukawa couplings are some dimensionless parameters in Lagrangian. We have no idea where these things come from. The biggest one is the biggest Yukawa coupling is for the top quark, and that's about 1. And the smallest is for the electron, and that's about 10 to the minus 5. And you might say, well, there's a pattern here. The first generation is lighter than the second generation. The second generation is lighter than the third generation. That's not a pattern. That was by definition. Okay. There's no pattern here, at least not there's very few hints of a pattern. Okay. People, of course, have tried to say that, oh, there is a pattern here, and they write some beautiful model of flavor. And it never quite works, but it's a nice try. You're still trying to figure this out. Now, the neutrinos are different. For the neutrinos, the term that we need is something like this. It's a dimension 5 operator, and so it comes with a mass out front, which I called m0. This is, in some sense, perhaps an explanation for why the neutrinos are very, very light, because you need a dimension 5 operator to write down the mass term in the first place. And this suppression factor here could be, I don't know, m Planck or m Gauss. There's some coefficients here, so there's really some generation labels, Fi, K, I, and K, and that matrix isn't too well known. We don't know the neutrino masses quite yet. We know a lot about their mass differences, and we know something about their mixings, but we are still in the process of understanding their detailed behavior. This matrix has essentially, with very few exceptions, no relevance for LHC physics, and so I won't discuss it. But, of course, it's very interesting on its own merits. Yeah?
How do you multiply the SU2 matrices? How does N come before?
Exercise for the reader. All right, there's daggers here. I mean, there's, okay. It's unambiguous. You've got two doublets, and they've got definite hypercharges. So there's only one way you can combine them into a singlet, and you square it, basically. I mean, there's another thing you could do, but basically that's it. Let me not get hung up on that for now, since it's not relevant for here. Okay, now let me emphasize what we know versus what we and what we suspect about this model. Okay, this is the standard model as we know it, or suspect it, because we don't really know this. All this story with the Higgs is exactly right. Well, what parts do we know and what parts don't we know? The thing we know is V. We know that electroweak symmetry breaking is broken by some kind of SU2 doublet. Because otherwise, you don't get the mass of the W's and Z's right. You don't get the various other things to work out right. We really know that. But we don't know if there's a Higgs boson, an H0. Not really. I mean, there must be something like it, because the VEV V should fluctuate. But this is complicated. For example, there could be not one Higgs boson H, but there could be 10 of them. And each of them has a small VEV, such that the sums of the squares, square rooted, adds up to V. And in that case, there would be lots of Higgs bosons, lots more than you're thinking. Because if I have 10 Higgs doublets, I don't have 10 Higgs bosons. Why did I get one Higgs boson from one Higgs doublet? It's because there were 3 extra particles, these goldstones, G plus and G0, which turned into longitudinal modes of the W and Z. That's done. If you add one more Higgs doublet, all 4 components of that doublet become physical particles. So with 2 Higgs bosons, 2 Higgs doublets, you have 5 Higgs bosons, 3 of them neutral, and one charge +1 and one charge -1, if you like, or if you like, one complex one. Okay. So the number of Higgs bosons could be much, 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 much larger, and there could be charged ones floating around.
So can't you just diagonalize them and then say there's one Higgs boson and then a bunch of scalar fields?
No, because so the question is, why can't you just say, well, I'll choose to define the object, capital H, to be the one which has the VEV, because, I mean, there's a multidimensional space here, but I can always choose what I mean by H to be the one that has Vev V. The problem is that that is potentially inconsistent with their masses and their couplings. In other words, what you want to do is you want to choose one basis that makes one thing nice, but it makes everything else awful. Right? So then there's no basis in which everything is good. You've got particles of different masses, and each of those particles with a definite mass has a different contribution to V, and may couple to the leptons or Qs in some different way. Presumably there's an upper bound on the number. I have no idea what that upper bound is. I haven't thought about it. Presumably there is. But it's a little tricky, because in addition to SU2 doublets, there could be additional scalars which are singlets under SU2 cross U1. And there's going to be very little bound on them. And they may or may not have VEVs. They can contribute to the potential for the Higgs. They can get involved in all sorts of ways in the Higgs sector. Higgs singlets. Okay, those can be complicated. Another possibility is that, this model is more or less right, but there is no physical Higgs boson. You will not be able to go out there and find a nice resonance, some sort of nice particle that is the H0, which is not there. That's possible. There's a question?
Why is it presumably an upper bound?
Why is it presumably an upper bound? Well, at some point, if you add enough particles to a model, their quantum effects will be big enough that they will somehow impact some property of the physics. But I haven't thought through whether that's really true or not. So I will cautiously say I'm not sure, but my guess is that, yeah, if you try to put 1,000 Higgs bosons, something's going to go wrong with data.
Certainly gravitational.
There's a gravitational upper bound, but there's going to be bounds from precision measurements already that are much stronger.
So how could you get a Higgs boson? Not get yourself Higgs resonance?
I'll tell you. Patience. If you don't know, then it'll come. But the one thing we know is that if I take the standard model as I have it here and I just remove the H, just the little H0, that's impossible if there's nothing else in the physics. That is to say, it is impossible that the only thing that's out there is the standard model as we have it written down and no little H0. And that's because the theory's inconsistent. There's calculations you can do within this theory that just don't make any sense. Okay, and this is the issue of perturbative unitarity. So if the theory has only the things I've given to you, then perturbation theory works, because there's no funny dynamics in QCD or in the electroweak theory at scales above the QCD confinement scale. Basically, everything's weakly coupled, so I can calculate anything. So in particular, I should be able to calculate W plus W minus goes to W plus W minus. You can even actually imagine measuring this, which either Jason or I will remind you of this later. But that's not the point here. The point is that this is a perfectly reasonable process, and you can access it at the LHC. And there are various diagrams. For example, there are diagrams like this one. I won't draw all the diagrams, where you have a Z or a photon. Okay, that's one scattering process. There's a 4-point vertex for the W's. And there's a diagram, for example, like this one. Now, what I'm telling you here is also true for WW goes to Z bosons. It's true for WW goes to top quarks. If you sum up these graphs, you get a perfectly reasonably behaved amplitude. If you remove this graph and you recalculate it, you find this amplitude grows with energy and violates basic principles of quantum field theory. End of game. Okay? This theory doesn't work. In fact, most theories don't work. If you just write down some random field theory and you're not careful with it, there's all sorts of pathologies. Field theories are rather constrained. Not as constrained as string theory, but they're constrained.
Well, so you really just mean that if you write strongly coupled...
I was very careful what I said. I said, this calculation breaks down.
Yeah.
Perturbation theory breaks down. Yeah. Or unitarity breaks down. One or the other. Okay? If perturbation theory is good, and I gave you a reason why it would be good in the standard model without additional physics, then this calculation makes no sense. And so the conclusion is either the Higgs or other stuff like it something to fix this unitarity problem is here. Maybe it's a Higgs boson, maybe it's other types of new particles. Or maybe the perturbative calculation is wrong, but that means new dynamics, and this theory doesn't have new dynamics. That means there's new things. Either way, there's new stuff. You can't just say, oh, this theory has new dynamics and say nothing else. That doesn't make any sense. We have the theory. All the dynamics is determined. All the terms in the Lagrangian. That's it.
But you say massive gauge bosons are not normalizable. You can generate an effective scale.
I don't like saying it that way. That's, I think, not really representative of what quantum field theory does. The statement that a theory is non-normalizable is simply the statement that to make sense of it, there has to be some additional physics in it. But that physics might not be new particles. It might just be new dynamics. But in any case, this theory, without the Higgs in it, is not a consistent perturbative theory. So we know there's something new. We don't know what its form is. And also, the other important point is where unitarity breaks down is near 1 TeV. And that tells us we need a TeV scale collider. So now we know why we need something like the LHC. All right, that is the first problem. And now what are the possible solutions? Well, one solution is there's a Higgs. One solution is that there's lots of, one possibility is there's lots and lots of W primes, lots of particles which are similar to W's, and they can appear in here in Z primes and so forth. There's a whole tower of them, and that can somehow resolve the problem. The third possibility is that perturbative field theory calculations break down. There's some strong dynamics of some new sort, perhaps new particles, but certainly new forces. And that just means this calculation has to be supplemented by a correct one. And finally, it could be just quantum field theory breaks down at 1 TeV. What we're really going to discover is the end of quantum field theory. And these are not mutually exclusive, in fact. Okay? But something is going to happen. Now, there is a second problem which I'll address. There was a question. Do you still have it?
Yeah. So I'm just interested to know whether these problems of unitarity, the breakdown of the perturbative calculation, does it always happen around 1 TeV?
Yes, and that's because you can calculate it within the standard model. That is to say, if I remove this graph, what I have left is graphs that just involve other standard model particles, and I can calculate them, and I can see where unitarity breaks down. Where probability gets bigger than 1 is pretty bad. Obviously, if I add other stuff, the whole game changes. But that's the point. If I've added other stuff, I want to discover it. Then we're already interested. Okay, it's not a problem. Okay, now there's a second problem which is really important, but is not nearly as fundamental a problem. And it's important to keep track of this. There is the perturbative unitarity problem, which says the standard model without an H0 needs to be supplemented by something. There's a second problem, which is called the hierarchy problem. And that is not an inconsistency. It is a discomfort-producing problem. It's not a mathematics breakdown-producing problem. What is the hierarchy problem? Well, I'm going to go through it very quickly right now, although we'll come back to it when we talk about ways to solve it. And most of you know what it is anyway, although I'm going to say it a little differently from the way you usually hear it, just for fun. So what is the hierarchy problem is basically a breakdown in dimensional analysis. Why does dimensional analysis work for physics? Well, it's not always obvious, although you get some essentially experimental sensitivity to this when you're doing calculations in undergrad and grad school. You discover that dimensional analysis usually works pretty well. Why does it work in quantum theory? Well, one way to say it is that quantum corrections are pretty good at restoring dimensional analysis, even if you try to change things at the classical level. Or better said, if you try to move the Lagrangian around so that some quantity is much smaller than you would expect from dimensional analysis, quantum corrections will come along and say, no, I'm going to put it right back where you thought it should be. You don't find in condensed matter very often, and when you do find it, you're really interested, quantities that violate dimensional analysis by a lot. And in the standard model, we don't really come into contact with this that much because all of the coupling constants that appear, all of the quantities that appear in the standard model, are dimensionless. There's the gauge couplings, and there's the Yukawa couplings. So they all should be of order 1. Of course, the electron Yukawa coupling is of order 10 to the minus 5. So why isn't that a problem? Well, the point is that there's a good reason in that case that dimensional analysis is violated. So we know that y top is of order 1. The electron coupling is of order 10 to the minus 5. What is the size of the quantum corrections to ye? Why aren't they of order 1? The reason they're not of order 1 is that the corrections to ye are proportional to ye. And why is that? Because in the limit that ye goes to 0, there's a new symmetry in town. When ye is 0, you can take the electron, let's keep it simple, the positron field, and you can rotate it by a phase, all on its own, without rotating anything else in the theory. And that rotational symmetry forbids a mass term for the positron. And at that point, you can see that quantum corrections are not going to violate that symmetry, well, at least not unless there's some change in the vacuum. But if you're sitting in the same vacuum, quantum corrections will preserve the fact that if ye is 0, delta ye will be 0. And that's only true if these things are, well, at least proportional. That's chiral symmetry. Chiral symmetry protects the masses of the light fermions. That's why not all the light fermions have masses of order 240 GeV. But this is not true for the parameter mu squared, which in the potential, which I never actually wrote down. In the Higgs potential, there's a parameter mu squared. I defined mu squared to be positive here to get the shape that I wanted before, which I've erased, but we'll need it again. Okay, mu squared determines the curvature here, basically, and therefore it determines where this v is. And v is mu squared over lambda. Now, the problem is often phrased that the Higgs mass gets quadratically divergent corrections. This is not wrong, but basically beside the point. We don't even know if there's a Higgs. So what are we worrying about whether the Higgs mass squared gets an infinite correct? No, this is not the point. The point is V. We know V. V is 246 GeV. And V is determined by this potential. And this potential is determined by dimensionless coupling lambda that could be order 1 or smaller, perhaps. But if perturbation theory is OK, it can't be much larger than 1. And by mu squared, which is the only dimensionful quantity in the entire standard model. And how big is delta mu squared? Which then would lead potentially to a correction in delta V. And of course, that's the thing which gets big corrections. And why should we expect their big corrections? Because by dimensional analysis, the corrections to mu squared should come from all different parts of the theory, including gravity or string theory, or anything else that's out there at high scales. And whichever is biggest should give the largest contribution to delta mu squared. This should be of order the maximum mass squared that any quantum effect can sample. For example, the Planck scale. So dimensional analysis would say this potential shouldn't look like this. It should either look like this, with a curvature of 10 to the 18 GeV, or it should look like this. Sorry, let me see if I can draw that better. That. No, I did it wrong again. Sorry. Let's try that again. It should look like this, and then come up way over here. That's what I wanted to draw. Okay. So that either V is 0, or V is of order m Planck. Those are the two options. The issue is not the Higgs mass. The issue is the shape of the potential. Either V should be 0 or V should be of order m Planck. And both of those are not consistent with experiment. So somehow, this isn't true, or something. It's not a mathematical inconsistency for there to be some tuning of the parameters of string theory such that this delta mu squared just happens to be really, really, really small. It's not inconsistent. But maybe it's not true. Certainly, it feels bad. Yeah? Maybe 25 years, 30 years of work. And we've only come up with one or two. All right? I mean, basically, it's hard to do this. And that's why there's all this model building, which we'll discuss in Lecture 5.
Would you restate it saying that near a critical point where electroweak symmetry breaking is stored? Closer to a critical point would be more.
Yes, we are closer to the point where the VEV goes to 0 than would be natural, given that there are scales in the problem that are of order m Planck. We do not have an experimentalist to tune the magnetic field close to the critical point. That's right. So the question is, who is the experimentalist who is controlling us and putting V at 246 GeV, and why? Okay? Good. All right. So again, I want to emphasize this is disturbing, but it is not a mathematical problem. It is a conceptual problem, whereas the perturbative unitarity problem is a mathematical problem and must be resolved. Both of these problems suggest that, first of all, there will be new physics at the TeV scale. There has to be, as you've seen. But also, that physics might be very rich, because if you just have the Higgs and nothing else, you've got this disturbing problem that the Higgs VEV V doesn't want to stay put. And somehow something should be there to prevent this argument from going through. Something should change the dimensional analysis argument. There should be a symmetry, as there is in this case. Or maybe the dimensions of this thing aren't what you think, and so forth. And so that's why we think it's very possible the LHC will not just discover a Higgs boson, but will in fact discover a very rich system of many particles, which all have to do with the resolution of the hierarchy problem. We don't know that, but we do know there's something there for the LHC to discover. Okay, good. So I've used most of the lecture to argue to why we need this machine, and now I want to talk to you briefly about its properties. And I'm running a little behind, so something will have to go in a later lecture, but that's the way it goes. Okay, so what do we need? We need a machine which can sample the TeV scale. It needs to be able to find a Higgs boson, help us explain electroweak symmetry breaking. It needs to find any other particles or phenomena that might be around the TeV scale to help us resolve the hierarchy problem. And it might be sensitive to dark matter, but we're not sure. So those requirements then determine how you build your accelerator and how you build your detector. And Jason is going to tell you about that. This brings us back to our 4 questions. Why would you build a proton-proton collider, first of all, when a proton-proton collider has to use protons? Protons. Ugh. If only any of these things were true for protons, it would be a much simpler world. A proton is, as in this TASI, you probably are already well aware, a big, well, not very big, but a messy, very messy ball with lots of quarks and lots of antiquarks. And yes, there are strange quarks in there, and lots and lots and lots and lots and lots of gluons, which carry a substantial fraction of the proton's momentum, incidentally. So this isn't true because there are lots of quark and antiquark pairs and lots of gluons. This isn't true because the quark-antiquark pairs carry some momentum and the gluons carry a lot of it. This isn't true because those quark-antiquark pairs certainly include strange and even some charm, even a little bit of bottom. Top so heavy, basically no. Quarks may be confined, but if I take a proton and I pull on this quark, it only takes a finite amount of energy for me to pull it out, right? It's not going to stay in there. All right, so I pull on it. What happens? Well, you get a little blob. Okay. What happens next? Pair production. Right in here, there's enough energy because at least 3 of the quarks are very light compared to 300 MeV. The energy density in here is large enough that pair production, just like electron-positron production in a strong electric field, this is up-up-down or up-up bar or down-down bar or strange bar production in a strong chromo-electric field. And the end result is that you get a meson and whatever's left behind. Okay, it may not be a proton anymore. It might be a neutron. But that quark came out just fine. Okay. They can escape. And that's really important for us, because when we smash protons together, we want stuff to escape. We want to see what we made in there. If the quarks were confined, then when we made a top quark, we'd never see anything. Or what we'd see would be very jumbled. It's very important for us that D is not true. Okay? It's just the way we talk about confinement that's a problem. And hopefully I'll get a chance to get back to that a little bit. Now, let's start our understanding of what it means to do proton-proton physics with a little discussion of a very classic QCD process. Sorry, very classic LHC process, which is not a QCD process, and for that reason it's a lot easier to talk about. And that is the production through a W boson of electroweak particles. Okay, so this is an electroweak process produced at a proton-proton machine. So, for example, we can take an up quark from one proton and an anti. And again, if protons only had quarks in them, we wouldn't be able to do this. But because protons have antiquarks, we can have a D bar from one of those protons combined with a U to make a W plus, which may be off shell, and that turns into an electron, a positron and a neutrino. Okay. Now, what can we say about this process? Well, first of all, notice we don't. It might not just be UD bar. It could also be US bar. Right? There's various processes which could generate this, but this one, UD bar, is one of the biggest because there are lots of U quarks in a proton. Now, let's consider a proton. Here's a proton. I don't have to explain to you why it's flat because you've already thought about that. Okay? It's highly Lorentz boosted. The proton has momentum capital P mu equal to E00E. And now the question is, what is the probability of finding a U quark in there that can initiate this process? Well, that probability can be, roughly speaking, defined. What I'm about to do is something known as the parton model. It is not completely correct, but it turns out to be close because of the properties of QCD. So what I'm doing is I'm treating quarks naively, and one has to do a better job for real calculations. But what I'm going to define is the probability of finding an up quark with a fraction x of the proton's momentum. And this is so again, this is the probability to find a U with momentum equal to x times p mu. Everything, the proton and the quarks, are being treated as approximately massless, which is OK at a machine as energetic as the LHC. OK, so then what do we do? Well, we calculate this process using ordinary Feynman diagrams. I leave that to you as an exercise. It's an easy calculation in the standard model. And we get an answer. And that answer gives us a differential cross-section, which is the cross-section for the up and down quarks, which in general I'll call partons. Quarks, antiquarks, gluons, all collectively they're partons. The partonic process has a differential cross-section, d sigma, d for differential, sigma for cross-section, hat for partonic. For ud goes to w, goes to E nu. And that is a function of the kinematics, which is a function of the U quark momentum, which is x1 p mu, a function of the down bar momentum, which is x2 p mu, and then the momenta of the electron, of the positron, excuse me, and the neutrino. Where's my eraser? Okay, we calculate that using ordinary Feynman diagrams. How do we calculate the rate at the LHC for this process? Well, the rate, the differential cross-section, for proton-proton to go to a W plus dot, 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 to go to an electron and a positron neutrino plus dot, 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 is equal to an integral over these fractions, dx1 and dx2. The probability of finding an up quark in the first proton, the probability of finding an anti-down quark in the second proton, and the differential cross-section, which I've written here. And then there are other terms. This is the term where the up quark's in the first proton and the down bar is in the second proton. There's another term where you switch them. There's another term where you have a U and an S bar. or a charm and an S bar. There's all sorts of terms, but this is the structure that they have. Now, this is always what we have to do with the LHC. There's a simple partonic calculation. Well, maybe not always so simple. And then you have to convolve that with the probability distributions for finding quarks and gluons of different types. Now, what is this dot, dot, dot? Hadronic crap. Okay? This is proton, proton. There's all the rest of that proton, and it all goes flying somewhere. Most of it goes flying this way, most of it down the beam pipe, and most of it, or down the other beam pipe, but not all of it. Some of it will get into your detector, and you better remember it's there. There could be additional jets radiated off the initial state. There could be all sorts of stuff. Don't forget this dot, dot, dot. It can determine the way the experiments are done. It's really important. And the best way to be naive about the LHC is to forget it. Okay, let's get the light on there for the last part of the presentation here. Hopefully everything will work without a hitch. Now, a couple of definitions that we're going to need here. How are cross-sections measured? They're measured in barns. One barn is 10 to the minus 24 centimeters squared. So a barn is a small thing, and we're going to talk about millibarns, microbarns, nanobarns, picobarns, and femtobarns. Now, how big is a proton? A proton has a radius of 10 to the minus 13 centimeters. So it has an area, and therefore a cross-section, geometrical cross-section, of order 30 millibarns. Okay, and that's the kind of stuff worth keeping in mind. All right, now with that, let's take a look at this picture. We don't perhaps have a, do we have a laser pointer? No. Okay. So this is the most frightening graph for the LHC that I know. If it doesn't frighten you, you're not looking at it hard enough. Look at the total cross-section. 30 micro, or really that's the inelastic cross-section, but the inelastic and elastic and total cross-sections, they're all of the same order. And then, oh God, I hope that stops. Ah, fantastic. Now I have to figure out what I do here. Which thing do I point? Push.
Press the green button.
Green button, great. Okay, so here is the production of a Higgs boson. Here is the production of a Higgs boson followed by the decay to 2 photons so you can see it. That is 100 femtobarns. That's 100 millibarns. 12 orders of magnitude. Even the W is 7 orders of magnitude down below the total cross-section. Okay. Stare at this and think about the implications. Okay? Here are some of the implications. Oh, by the way, why don't we look for the Higgs? When the Higgs is light, what does it most dominantly decay to? Someone's calling to let us know. What does the Higgs decay to if it's light most often? Decays to the heaviest fermions available, that's BB bar. Why don't we just go looking for Higgs goes to BB bar? There's the BB bar cross-section. There's the Higgs cross-section. I don't think so. The standard model processes which go on in proton-proton collisions make new physics processes just almost vanishing. They're just incredibly small. How are we going to deal with this? Well, we have to have a collider that produces an enormous number of collisions. Because if you're looking for something that's at the 10 to the minus 12 level, you better have 10 to the 15 collisions. And we will. Now, there's a problem with that. We can't store 10 to the 15 collisions. 10 to the 15 collisions means you need to make millions to tens of millions to hundreds of millions, even billion collisions per year in the highest luminosities. And billion collisions per second. And you can only store about 100 or a few hundred at best. You are throwing away, because you have no choice, 99.9999% of the data as fast as it comes in. Got that? Let me say it again. As fast as those collisions come in, we have to throw them away, because otherwise we'll never get enough of them, and we'll never be able to find the Higgs. This has to be done by a system, an automated system that looks at the events as they come in and makes a decision. And that system is called the trigger. And if you don't understand the trigger, you don't understand how these machines work. The trigger has to be smart and not throw away what you're interested in by accident. Because if it throws it away, it's gone forever. The collision might as well never have happened. It hasn't been stored. So if we theorists aren't smart enough to think of all the things that the LHC experimentalists should be looking for, and there's some really new interesting phenomena they don't trigger on, they will never find it. Theoretical bias enters at this point. Now, on top of that, they're still collecting 1 billion collisions per year. So how do you look for things when you have 1 billion collisions per year? Well, how many graduate students do we have? Okay, we divvy it up. I don't think that's going to work either. It's data mining. You have to dig through that data for what you're interested in. And you need an automated system to do that. I mean, it's an automated system you have more control over. The data is on tape. But still, if you don't ask the right question of 1 billion events per year, you will not get the answer. So you have to ask the right questions. And there's software and conceptual questions and techniques which are typically used. And if the theoretical community doesn't come up with the right types of ideas, maybe that huge pile of data will not be used properly. And so there'll be new physics in there. No one will find it for decades. Maybe they'll find it eventually 150 years from now, but that's a little late for you and me. Right? Again, theoretical bias comes in here. So the theorists are really important here, and we can really screw it up. Okay? Now, the last thing I want to mention is that everything that can go wrong will go wrong at these experiments. It may go wrong very rarely. Oh, maybe only 1 in a million collisions, something screwy happens. But 1 in a million is 1 million times more often than Higgs goes to gamma gamma. You have to worry about every possible fake detector problem, electronic issue, and they spend a lot of time on that. Big backgrounds to new physics are not always things that you and I can calculate. They may be things that have to do with the way the detector works. And so this is why, given the complexities of this machine and all the subtleties that are involved, you need to pay close attention to Jason Nielsen's lectures, which are far from what you know. But if you want to understand the data as it comes out of the LHC, if you want to understand the plots you're looking at, if you want to understand the discussions that are going on, you need to understand how these accelerators and detectors actually work. That's enough for today.